Hi students. So in this lecture I am going to explain the frequency and the temperature effects of all the polarization mechanisms. So when the field is applied to the dielectrics, the polarization occurs as a function of time. So the reorientation of the dipoles in response to an electric field is characterized by the relaxation time. Relaxation time is the time taken for the polarization process to reach 0.63 of the maximum value of polarization. The relaxation time is varies for each of the various contributions to the polarizability. Frequency effects. The electric polarizability. It is a very rapid process and will complete at the instant the voltage is applied. The reason is that the electrons are very light particles than ions. Therefore, even for very high frequency applied voltage, this kind of polarization occurs during every cycle of the applied voltage. The relaxation time is small for the electronic polarizability, but response is very fast. Next, ionic polarizability. Response is very slower than the electronic polarization because ions are heavier than the electrons. So in the optical frequency, the ionic polarization is absent. If the frequency of the applied voltage is less than 10 power 13 Hz, that is infrared range, the ions have enough time to respond during each cycle of the applied field. So it exists up to the microwave frequencies. Next, orientation polarizability or dipolar polarizability. It is this response is very slower than the ionic polarizability. Ionic polarization. Sorry. The relaxation time for this case varies with respect to the dielectric materials. The polar molecules in a liquid easily reorient themselves than the solids. So this type of polarization occurs in audio and radio frequency ranges alone. In microwave frequencies, the orientation polarization is absent. Okay. And next one is space charge polarizability. The response is quite slow and the relaxation time is very large because in this case the ions have to diffuse over several interatomic distances. So this process occurs at very low frequencies in the order of 10 power 2 Hz. So we observed that at low frequencies less, uh, less than 10 power 3 Hz, all the polarization is exists. So therefore total polarization has the maximum value. At visible or optical frequency range, only the electronic polarization is exist. The remaining ionic, dipolar or orientation polarizability and spatial polarizability is absence. So it has the less value in the visible range. Next, temperature effect. The electronic polarization and ionic polarization are independent of temperature, whereas the orientation and space charge polarization are temperature dependent. In orientation polarization, it decreases with the increase in temperature because The randomizing action of thermal energy decreases the tendency of the permanent dipoles to align along the field direction. So the epsilon R decreases. But in spatial polarization, when the temperature is increased, the ions can easily overcome the activation barrier. So therefore, it gives a rise to polarization. So therefore, when the polarization is increased by spatial polarization, in this case, the dielectric constant will increase with the increase in temperature. Okay. And it is pictorially represented by the graph. Okay. And next one is dielectric loss. So if a dielectric is subjected to an electric field, the electrical energy is absorbed by the dielectric and certain quantity of electrical energy is dissipated in the form of heat energy. This is known as dielectric loss. This loss occur both in direct and alternating voltages, but the direct dielectric loss is less in DC voltages than the alternating voltages. Okay. If an AC voltage is applied across the capacitor having the vacuum or purified gas, then the resulting current and the voltage as the angle difference is 90 degree. That is, the current leads the applied voltage by 90 degree. Therefore, power loss is equal to the PL is equal to VI cos theta. Theta becomes 90, therefore power loss is equal to 0. So there is no loss when we use the purified gas. But in commercial dielectric, that is practical dielectric is present. The current leads the voltage by 90 minus delta degrees. Then it shows that there is some loss in electrical energy, and it is explained by the power loss, and the delta is called as loss angle. Okay, and shown in the above figures. Okay. In this case, the power loss is equal to VI cos theta. Theta is equal to 90 minus theta. Therefore, cos 90 minus theta is equal to sin theta. Therefore, power loss is equal to VI sin delta. We know that by Ohm's law, V is equal to IR. Therefore, I is equal to V by R. Here, R is replaced by the reactance Xc. That is the capacitive reactance Xc. So, therefore, it is the power loss is written by PL is equal to V squared sin delta by Xc. Xc is the capacitive reactance. We know that the frequency the oscillator is equal to 1 by 2 pi RC. So R is replaced by XC, therefore 1 by 2 pi XC into C. Therefore XC is equal to, by interchanging XC and F, therefore 1 by 2 pi FC. Therefore power loss is equal to 2 pi FC V squared sin delta. If delta is very small, sin delta is equal to tan delta. Therefore, power loss PL is equal to 2 pi FCV square tan delta. If C and V are constant, 2 pi F are also constants. Therefore, naturally the power loss varies with the frequencies. The power loss at various frequency ranges as shown in figure. In the electrical frequency regions, the power loss is high due to the diffusion of ions from one equilibrium position to another. In the optical region, the power loss is less because here the dielectric loss is associated with the electrons. The power loss value becomes PL directly proportional to tan delta. Thank you.